Hello, hello.
Hello, I'm John, and
I'm Karl.
we are two of the tutors for the online course COMP1 being offered by UNSW. We are here today to do a quick little video on the AsciiBrot exercise. So if you want to explain what we'll be covering.
So we'll be going through four things today. Hopefully we'll have covered the major concerns that most people had or confusions. First of all, we'll be going through what a struct is and how to use them. And that'll be John. They'll be kind of explaining how the scaling works between your program and the mandelbrot set. And then I think we're just both going to kind of talk about how to do zoom, or not really tell you how, but kind of give you a few hints, because that is the challenge exercise. And then we'll be showing you a few cool things that you can do and that you will be doing with the mandelbrot set.
Cool.
So let's get started.
And as always, if you have any issues, please continue to put them up in the forum. We will reply as soon as we can. But we really appreciate the feedback, and also your fellow student is often the best form of support you can have. So if we haven't covered anything correctly here, please help each other, and everyone will reach the state of proficiency.
And feel free to tag us.
Yeah, tag us if you need some help. Okay, so what we have here, we have the exercise code on the left-hand side. This is the struct version. On the right-hand side, we're going to have a quick discussion about a few concepts. The first of which is type defines, which is an important concept to understand to do structs in a way that's easy for other programmers to understand what you're doing. So a type definition is, by its definition, a way to define a type. So the types you currently know are things like ints, doubles, floats, characters. These are types which the compiler knows about and which you can use in your programs to store data. If you want to create your own type, you can do that using a type define. So here we've said type def double num. If we break that up, type def just says we're about to write a type definition. The next thing you write is a type, which currently already exists. This can be a basic type. In the case here, we have a double, which is a basic type. Later on, you'll see you can also use the complex type, or something like a struct, or even pointers and things like that. Then we've given it an identifier. So we've said here we want to type define a double, and we want to call that new type to be num. So for all intents and purposes, wherever we create a variable, we can create it of type num, and it will then be as if we're using a double, however, it's our own type num. Yeah, so we've got a struct point here. Ignoring structs for the moment, if we went into our main function and we then wanted to do some simple things like, oh, sorry, I'll put it on different lines. So if we said num a equals 1.5, num b equals 2. So because num is type defined as a double, it can store any information that a double can. It will act as if it's a double. However, later on, for example, if we wanted to change this to float, then everywhere in our program where we've defined a variable of type num, it's now as if it was a float. So this can be powerful if you are doing certain mathematical calculations, or if you any type of data you want to store in your program.
If you want to make it clearer as well.
Yeah, if you want to make it clearer. One thing that I sometimes do in a program, you don't have to do this. One time, you can see this around, is I will often type def an unsigned char to be a byte. If that doesn't make sense to you, don't worry. Sometimes it's helpful if you're dealing with raw memory to think about it in terms of bytes instead of an unsigned character or a char. So that's what a type def is. And some of you may be wondering, well, how is that different to a hash define? So, for example, why can't I just do a hash define which says, now I always forget is this? No, it's the other way around, isn't it?
Yeah.
I always get confused with that. So what happens if I just want to hash define, I'll do this for a way that you guys know. If I want to hash define num to double, well, that will work. However, what you're losing is what's called type checking. So if you use a hash define, your compiler doesn't know that the identifier num refers to a new type that you want to use, which is of type double. Which means that if you declare a function, you could then set or receive certain variables that you don't really want to receive those types. So, to kind of shrink it down, the more appropriate way to do it is to use a type def, because then your compiler can do things behind the scenes that will help you and will bring up warnings if you're starting to use behavior which is not or could potentially lead to issues. Does that all make sense?
Yeah.
Cool. Okay, now structs. A struct is a way of collecting variables together that are related. It's a way of taking multiple bits of data that form something logical that we consider as humans or as programmers. We take some logical data that's connected and we can then look at it as a single entity. So the example we've written here is we have a struct point which contains two numbers or two nums, x and y. It makes sense for us to think of a point as a single entity. You have an x coordinate and you have a y coordinate. If we didn't have struct, we would have to do something like this. So we've written here num A, num B. We would have to do something like x and y equals 1.5 and y equals 2.
And then you'd have to pass them in as separate entities into functions.
Yeah. And
separately.
if you had two different points, you'd have to then go AX, AY, and BX and BY. And then imagine if you wanted to deal with 100 points. Well, how are you going to do that? It's going to be messy. There will probably be errors, and it doesn't make sense. And there's a whole lot of copy pasting of it's a messy way of doing business. Instead, what we can do is create a struct point A. Let's just call it A. And then we can say something like AX equals 1.5 and A.Y equals 2. So here we're saying that struct point is a type or a structure which contains two variables of type num, and there's an x and a y. And to use those, we simply say A dot, and that will then reference the x variable and the y variable in that structure. If we wanted to create another, we could go struct point B and say, okay, well, b.x equals 3 and b.y equals -1, and we now have 2 points. If you wanted to be clean, you could even do this.
Yeah, and you can also do the standard arithmetic operations that you usually do on.
Absolutely. So if we wanted to say something like struct point C, we could then say c.x equals a.x plus b.x. And we could say c.y equals a.y plus b.y, and that's very interesting. So as you can see that we've added 2 points together, and we've put that into a new struct. Now, what we can even do is we can take this. In fact, I'm going to need this as well. So struct point result, and result equals add point of A and B. Bear with me here, and return C. So as you can see here, we've now created a function which will add 2 points together, and you don't have to deal with the messiness of saying, okay, x coordinate plus this, 1, and blah, blah, blah. And you now have this which will work for all of them as soon as I change things to the correct parameters. So that's more or less how a struct works. It groups related variables together.
A few people, when they first learn this, are often ask what's the difference from arrays as well, and that the difference, like why wouldn't you just use an array for a struct? And John's typing out.
You can have anything. You can have all different. There's no reason why a struct can't even contain another struct. So if you have a struct point, it could then also contain like a struct whatever awesome struct. You know, A. There's no reason why you can't do this.
Also, usually in a struct you'll have related variables, but not necessarily variables that are the same to a certain point.
Yeah, absolutely. For example, if this was a vector, you could even add something like a num length in there, which, yeah. One other point, to tie type defs and structs together, and we're getting near the 10-minute mark, so we'll have to wrap up our talk on structs. But what we've got here, struct point, we can use a type def and then do something like this. Yeah, I'll do the... So what this does, and I'll explain to you another convention that we use at the moment. So as you saw in the beginning, we had type def, we then had a type, and we then had an identifier for what we wanted to call that new type. Here, we're saying type def, our type is of struct point. and our identifier is point. Now, because to some this can be confusing that you have a point up here and a point down here. In C, they're two different things. Struct point is different to point. That's why we're using a type def, because we don't want to, here we've had to write struct every single time we do it, and that's, to be frank, that's quite annoying. So if we want to take the struct out here,
we'll just type def it.
And here there should have been a struct in front of here and so on and so forth. But now, because we've typed def this to point, it will be, it will work the way we want it to. And also, as a matter of convention, to stop any confusion, we usually put a underscore, or some people usually put an underscore in front of the struct name here, just to make it more explicit with what the struct is doing. So that's structs.
Arrow operators as well.
Okay. So in the example you've seen here, one common way of dealing with structs is to deal with them as pointers to structs, because as you know, whenever you pass a variable in that's passed by value, and that's most of the way that you've been passing variables, that's anything that's not passed as a pointer is passed by value. And in that case, it has to copy the entire data structure, which for a structure, it can be quite a large data structure. So the convention is to pass a pointer to a struct as the argument into a function.
In this case, it's not as bad because you've only got two elements of the struct, but sometimes you can have like hundreds or even thousands or hundreds of thousands.
Yeah, so yeah, that's exactly right. So here, in the example code for the exercise, you'll notice we haven't returned anything. And that's because when you're dealing with a pointer to a struct, you're actually changing the data in that struct, so there's no need to return that struct later on. The way we deal with this is we say point, and if you see that the struct here is pretty much exactly identical, apart from we're using doubles instead of a type def. And we're passing in a pointer to a point struct. So what we do here is we need to dereference this pointer in order to access the variables in the struct. So here you'll see the p and then the arrow operator, or it's a hyphen and greater than symbol, x equals x. And that is equivalent to what we have here. Now you've dereferenced pointers before, so you will see that this is identical. The way we have p arrow operator x equals x is exactly the same as saying in brackets asterisk p or dereference p dot x, as we use in our original example on the right here, where we said c dot x and so on and so forth.
It's pretty much just saying the value pointed to by p dot x. So,
and so to pass this into this function, if you had a point A, to pass this into set point, you could say set point and A, remembering that we need to pass in a pointer to a point and not just a point itself. And then you could do this, and then that would set the x and y coordinates of A to be 10 and 5. If there's any more questions on structs, we will be more than happy to answer them in the forums. If you're not comfortable with structs, feel free to use the non-struct version to complete the exercise. However, you will find that you will need structs later on in the course to do some of the exercises. We've introduced that a little early here. Those of you who have already done it with structs, that's awesome. Those who haven't done it yet, don't worry.
There's a non-struct version that we've put up as well.
Yeah.
It's just a bit more cumbersome to use, and it'll be a bit uglier, I guess. Okay.
Right, so moving on.
Yeah, we've done structs.
Let me just get the tablet. Alrighty then. And I need to change my color. Achievement unlocked. First 14 minutes of the video.
Okay, so now I'll try and explain how the scaling works. So, in the mandelbrot set, you've got a set of coordinates. They're called Cartesian coordinates, right? And your origin is 0, 0. No, the mandelbrot one.
Oh,
so your origin is going to be 0, 0, and then like the top right, for example, say your top right is going to be 1, 1, and your bottom right is going to be 1, negative 1, etc. However, since your program is printing it from top left, going to the right, then from line to line, you want the origin at the top left for your program. You know, when we were doing the flag exercise, you started with I and j at 0, and 0, 0 would be the top left, right? So we want a way to kind of convert these coordinates and work between these two things, the program coordinates and the Mandelbrot coordinates, the mathematical coordinates, right? And this kind of change of coordinates is called a transform. And so we've got a little... yeah, we've got... Oh, no!
I have to log in.
We had a sound of a transform.
You probably can't even hear that.
Yeah. Well, we've got a picture of a transform. That's good. So I'm sure there's quite a few ways of doing it, but this is probably one of the easier ways. So if you're having trouble, just follow this method. So what you're going to want to do is... Oh.
I'm just changing the color.
Okay, so...
We're going to start with this one?
Yeah. You're going to want to go through a certain few steps. So
just as an overview, we want to take this point in our program, which is a character. It's the bottom left character in your Mandelbrot.
Yeah.
And then...
convert it to be the bottom left. As in, the character where each could either be a star or a space.
Yeah.
So we want to convert 0, 30 to be negative 1.5, negative 1, so that you can kind of check if it's within the Mandelbrot set or not, within your Mandelbrot function. So first what we'll be wanting to do is to be finding the relative position of the point on the canvas or a screen. So what you'll be wanting to do first is you find, we'll be dealing with the x-coordinates first of all. So you find from a scale of 0 to 1 where this x-coordinate is. So you kind of get a fraction of the screen. So say a point was in the middle, it would be half, you'd get half for the x-coordinate because it's halfway through the screen. And if it were 3/4, it'd be 0.75 because it's 3/4 of the way through the screen. So the way you'd be doing that would be you first get your program coordinates, and then what you'll be doing is you divide that by the range of your program. So for your x-coordinate, say you had 0 as your x-coordinate, you'd be this isn't really a good example because 0 like
it will work out when we
yeah, we'll do
when you have to look at this.
Yeah.
So
you want to find like what percentage of the screen across or what fraction of the screen the x-coordinate 0 is for your program. So 0 divided by the length of the screen will give you that. So the width of the screen.
If we might want to cover the ranges as well. So for this we have the x and the y, which the x is a range of 72. This is a range of 30.
Yeah, this is what I'm talking about when I'm saying width. It's just how far across you've got. And
so the x, and do you want to go through how to get the range?
So for the Mandelbrot, to find the range, it's a bit harder because you're not starting at 0, so you can't just grab the number that's all the way to the right. You've got to find the difference between your leftmost number and your rightmost number, and your bottommost number and your upmost number for the y-coordinate. So for the x-coordinate, for example, we'd be going... we'd be finding the difference between 1 and negative 1.5, and that's 1 minus 1.5, which is a bit confusing, but that just gives you 2.5, because the difference between negative 1.5 and 1 is just 2.5. And for the y-coordinate, the height, or the range of the y-coordinate, is going to be the difference between 1 and negative 1. So that's 1 minus 1, which is 2.
So that's our equivalent ranges.
Yeah. For the program, the range is super easy to find because your top left coordinate is always going to be 0, 0, because that's going to be your I and j values.
Yeah.
When you're iterating through your while loop.
So what I've drawn up here is these are the different ranges that our coordinate is going to go through. Starts off for the x coordinate. It's going to start as a value between 0 to 72, and that's one of the characters in this. So it's going to be somewhere it lies in there. We're then going to, as Karl said,
0 to 1.
Divide that. So whatever the x is, we're going to divide our x by our maximum value, which is 72, to find, and that will convert it between 0 and 1.
Yeah, which gives you the fraction of the screen as across.
Yeah. We're then going to multiply that by our range, which is...
the Mandelbrot range.
The Mandelbrot range, which we got over here, and this is 2.5. That will then put this ratio, so if this was halfway between 0 and 72, this is now going to put it halfway between 0 and 2.5.
Yeah, so you're kind of just scaling it and make according to the length. So
we can then go into so do you want to do the example with 0?
Sure.
So 0 divided by 72 is
0.
No prizes for that one. It's 0, and so that's 0. Now this value here is our value between 0 and 1.
The fraction of which I've said that a million times now.
We now want to multiply this by 2.5, which is going to be 0. This now is at this stage where we're between 0 and 2.5, but that's not good enough. We're not at our negative 1.5. So obviously, if we're converting a 0.030, we're taking this 0. We need it to get to negative 1.5 at the end.
So you've kind of got we're just kind of looking at it as if it started at 0 all the way to the left, but obviously it didn't. So you've got to correct that offset. You've got to shift it across however much it is. So you've got to minus 1.5. So that'd be 0 minus 1.5.
Well, just to make it clear,
plus minus 1.5.
if you add the minimum, because the minimum is a negative, it becomes a negative. So 0 minus 1.5 is
equal to minus 1.5.
1.5.
And that gives you your x-coordinate in terms of the mandelbrot program. And now you can, if you get the y-coordinate, which we'll do as well, you can just you can kind of just feed that into your mandelbrot function, and the function will just determine whether or not it's within the set or not, because obviously you can't use your program coordinates. That just won't work.
So let's use something like this.
Yeah, let's do 30.
We want to get this 30 y-coordinate, and we want to convert it into
Negative 1.
-1. Now, as you can see, we're doing this on the corners, but there is no difference between what we're doing here. As a final example, we could
We'll
even
do
do
the center.
the center point.
Okay, so okay, let's go 30, and then we divide it by the height or the y range. So that's 30. So what's 30 divided by 30?
And if anyone's wondering where we get this 30 from, that's so up here we've got 0 to 72, 0 to 1. Well, this here is 0 to, and instead of 72, this is actually the maximum of the axis that you're dealing with. And this here is the maximum of the axis. Sorry, no, this is the range.
It's just, they're both the range. They're just, the width and the height of your thing depend in regard to what coordinate you're using.
Okay, so let's write this. So this is 0 to the range. Oh, I can't even spell. That's awesome. Range. This is 0 to 1, and this is the range. Whereas the first one, this is your program.
Can you kind of draw like?
In fact, let's do this. I'll do it color coded. So we've got red for program and blue for mandelbrot.
If you just kind of show that it's just like across like that.
Yeah, sure, I can do that. So the range here is this distance here, which we know is 72, or it's in this case 30. So this is the range of the axis that you're currently dealing with. This here is always going to be 1. Whoop. Now if we change this to mandelbrot range, which is going to be this. Okay, keep that.
So that's your y range and your x range for the mandelbrot. Okay, where were we at? Oh yeah, we were dividing 30 by 30. So I was figuring it out this whole time. Thankfully, John bought me a bit of time, but I determined it to be 1.
Okay, we have 1.
Okay, so now what this is saying is that this is all the way down your program range, all the way down your y-axis. Now, what we want to do is we want to multiply it by the y range, right? So what's our y range? It's 2.
Which is 2.
Yes. Also, you'll have noticed that for the y-coordinates, we're going downwards for the program because, that's how it works. You're just going to, your program's going to be printing the top, then the bottom, so it's more convenient for the program. However, for the mandelbrot set, it's convention in mathematics to go Cartesian coordinates to go from lower to upper, so you'll have to account for that too, unless you want to print a flipped mandelbrot, which I don't think matters, does it?
It depends what level of zoom you're at, but it can matter. But yeah, it's good to have it flipped around the right way.
Okay, so so this is telling us. Well, yeah. I forgot to mention that you'll have to multiply it by negative, since you'll be flipping it around.
Yes.
So just add in... Oh, no, not for the x coordinates, just for the y. Because the x you
That's a
don't
very
flip
good
around.
point. Very good
Yeah.
point.
So now you'll get negative 2. The reason is, as I just explained, the y coordinates are flipped around, so if you multiply by negative, it'll just flip it around for you. So now you get negative 2, which is the relative position if we were going from...
Okay, so what have we got? We've got the add and minimum, so we have negative 2.
Yeah.
We then want to add the minimum, so this is a mandelbrot minimum. So the minimum is negative 1, which something is wrong there.
Something went wrong. So we've got 1, and...
I think you'll find we don't need to multiply it by negative here because we've already accounted for the...
No, it should.
What have we got here? So this is going to be negative 3, which obviously doesn't work out. It should be negative 1. This should be a... it should be a plus.
We confused ourselves.
This does work out. If you... No, it doesn't.
No, it doesn't.
Because then you need to...
Okay.
What have we done? This is a prime example of what happens when you don't pre-record things and you actually try and work them out on the fly. Well, let's have a look. Let's try and work out where we've gone wrong here. We've got 0, 30. It is the bottom, so the range is correct. We have 1 being multiplied by a range of 2, which is also correct. It goes from 1 to negative 1.
Mm-hmm.
Then we...
Oh, it's because
we don't actually... We don't need to do this yet.
No, it's because you're flipping it around. Yeah, you don't... like, you're at negative 2, which is all the way at the bottom. And then...
Because this has no concept of being flipped yet. This is just a range between 0 and 2.
Yeah. And then you're adding... You're meant to add... You're actually meant to subtract 1. Because... like, it should be
so
negative 2.
Negative 1.
Yeah.
Ah, okay.
Yeah.
That makes a lot of sense.
Yeah.
So, just to clarify for anyone who got lost in that incredible train of thought we just
Okay,
had
let's just, kind of wipe it all and start again.
So,
we
don't feel bad if you're getting confused by this because we know, well, we semi-know what we're doing and we still got it wrong in the video.
If you're uploading this to YouTube, we should have kind of an annotation that's like skip all this.
We're just like...
It's confusing.
Yeah. Okay, so it is multiplied by negative 2.
Yep.
So this does equal negative 2.
Yep.
So this is negative 2, negative 1.5. So this actually...
Negative 1.
Yeah, sorry, that's what I meant. So on the top, that would have been not a plus negative 1.5. That is actually a negative 1.5, which then should have equaled 1.5.
No, because when you've got your x coordinates, those aren't flipped around as opposed to your y coordinates.
Okay. I'm with you.
I'll have to think about this later, but yeah. Needless to say, you should...
Well, let's put this in and let's test it with the other coordinates and
Yeah.
we'll know if it's correct. This is the best way to test things. If you're unsure, take something which you know is correct, find a working example, and then take something else you know is correct and make sure that it's working for both of those. So negative 1, which is going to equal negative 1, which is the point which we wanted.
So now we're at negative 1.5, negative 1.
And let me just fix this up because this is actually the range from the mandelbrot. I just wanted to make that explicit. And this here is actually the
Offset.
The minimum offset from the mandelbrot too. Well, as an example, we can now do the center point just to test that this is correct.
No, that wouldn't work because the center point is at the center, so it doesn't matter if you flip it around or anything.
We could do...
Let's do 1810.
1810. Great.
You'll need a calculator.
Great example. So we're going to do 1810. So it's going to be 1/4 of the way along here, and 10, which is going to be 1/3 of the way here.
10. It's there. Because
This goes up. So this is 10, 20, 30.
Oh, right, yeah. Sorry,
So-
I was looking at the 15 as the range for the y.
Okay, so we're looking at a point here, 1810. So let's do the x-axis first. So we're going to have 18 divided by 72,
yeah.
which is going to equal 1/4.
Yeah, which...
So we're at this stage here. We've now got it between 0 and 1.
Mm-hmm.
We now want to multiply that with the range, the x range, which is 2.5. So that is going to give us 2.5. So that's going to be 2, which is going to be a half, multiplied by
0.
another half, which is going to be...
Let me get my phone and get the calculator.
Here we are.
It's
going to be a half, then plus a half.
I can't.
So what's 0.625?
Wait, what was the amount? 2.5 divided by 2, yeah?
I think it's 0.625.
Yeah, probably. 2.5 divided by 4. 0.65.
0.625. Okay, so we're now at the stage where we're within 0 and the x range for the mandelbrot set. This is not our proper correct coordinate, however. We now need to shift it by adding the minimum. The minimum here is negative 1.5. So we have 0.625
minus 1.5.
Minus 1.5. Minus.
No, minus, just minus.
Because it's the x and not the y. Okay, this is awesome.
Calculator again.
Which, that's going to equal 0.8 to negative 825, I believe. Let's just double check.
Negative 0.875.
875. Terrible. Terrible at the math. Let's just rub that out so you don't see my horrendous mathematical error there.
This is what happens when you do too much.
This is why we can't have nice things. So that there is our correct x coordinate. So if we put the little point in here, bloop, 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 it's... wait, that's...
Negative 0.875, which makes sense. Yes, it's kind of in between negative 1.5 and 0.25. Yeah.
It's going to be closer down this end, though.
Yeah, but we haven't done the y coordinate yet. But it's correct for the x coordinate.
Oh, of course, yes, because we... Yes. Okay. Woo! That was exciting there for a second. So, yeah, this is around about negative 0.875 for the x coordinate, because you can see this is negative 1.5, so it's weighted more heavily on the left-hand side. Cool. Y coordinate.
Okay, so for the y coordinate, what was 10? So we'd go 10 divided by the y range, which is 30.
Which equals 1 over 3. That's nice.
Oh no, it's gonna be terrible to work with.
1 over 3 multiplied by the range.
The y range, which is 2. Negative 2.
Negative 2 because we're flipping the y-axis.
Let's keep it in decimals for now. 2/3. Minus 2/3, yeah.
In fractions, you mean?
Yeah.
So negative 2/3. We now want to add the minimum.
Yeah. But no, you'll want to minus the minimum.
Minus the minimum, which is going to add it.
Yeah.
Which becomes
plus 1.
1.
Which is negative 1/3.
Which is 1/3.
Negative 1/3. Oh, yeah, 1/3. Which is 0.3. Which should mean that it is a bit above the 0 x the 0.
Which is where it should be. So here's the middle line. It should be 1/3 between here and here, which is exactly where we want it to be. If this is 0.33333 recurrent. So there you go. The formula is correct. So the things you need to note there, or at least the thing I got out of that video, the x-axis, nothing is different to what we said here. Divide by the program x range, or the axis range, multiplied by the mandelbrot range. Then take that value and add the minimum. For the y range, the differences are you multiply
by the negative
y range, and you then you subtract the y minimum here, which will then get you where you need to be. Now I'm just wondering if we were to is this another way you could do it? Instead of multiplying by the negative range, you could say multiply by 2, which would get you 2/3, and then take the minimum and subtract that. Is that always going to work?
I don't think that would. If you had, for example, the 30 that goes to 1, and then multiplied by 2, that's 2. So then you've got negative 1. Negative 2, which is negative 3.
Okay,
so
that's fine. Okay, well at least now we have a working method. So that is one of the ways in which you can scale. And the way we've done this is, like I was saying, we've taken a relative position, we've scaled the program coordinate or the program character, x and y, into a range between 0 and 1. And we've then multiplied that out to basically extrapolating, because 0 to 1 is what's called normalized coordinates. You then extrapolate out a normalized coordinate into whatever range you want by multiplying by it. And then we've shifted that because we're not interested in a 0 to this range. We're interested in whatever range we have, which is negative 1.5 to 1. So by moving this point left enough to meet that minimum is what we want. So here 0 minus 1.5 is going to give us 1.5. So any value in this range minus 1.5 will give us the value we want.
And
that makes sense.
Yeah, we kind of got confused with the whole flipped thing, but
it's confusing.
I'll post an explanation as to why this happens after I've thought about it a bit.
If it does confuse you, one way you can do this without having to do the flip is by changing your axis in the program.
Yeah, you could simply have your whatever variable you have as your y coordinate. Yeah, you just decrement it until it reaches 0.
And this is why you can do it multiple ways. Your coordinate systems are a completely abstract idea. It's a way of you deciding how you reference certain points. So if one way doesn't work for you, change it to the way that does work for you. If starting at 0 and increasing the y value as you go down doesn't work, then start at your maximum y value and decrease as you go down.
And it's all really the same idea. The hard part is the conversion from one coordinate to the other and figuring out, do I multiply by the negative? Do I add or minus the offset? All you have to do is think about it a bit. But once you've got the general idea of it, it really is very simple. And once you've got the general idea of this, you'll be able to do the whole task, just knock it down in one go.
Because the cool thing is here we're dealing with fixed values that were given to you in the exercise. To do task 2 and to do the challenge with the zoom, more or less all you're doing is taking those fixed values and making them a variable. And so instead of, for task 2, one hint, if you would like to do task 2, I have something popping up. If you want to do task 2 is, obviously, if you want to be able to move the view, your minimum x is no longer going to be negative 1.5. Your minimum x is going to be
whatever you want it to be.
Whatever you want it to be. And it's still going to be the same scale because you haven't modified the zoom. You've just changed the x and the y ranges and the minimum and maximum. As you saw before, a range of an axis is merely the maximum that you can have. For that.
I'm just kind of freaking out.
That's all right. The range is simply the maximum minus the minimum. Yeah. Okay, so that's how you move it. You can also use another method for calculating the movement of... Stop doing crazy stuff.
Pen's freaking out.
There is another way to calculate that, and that is to deal with the center point of the program and the center point of the transform of the mandelbrot. We won't go through that here, but that is another way you can do it. And that essentially you need to work out how many units are in between each character coordinate, and that will lead you directly into zoom. Do you want to cover?
Oh, we can both do it.
Okay.
So the way that zoom's going to work, I'm just going to wait a bit.
Let's just get this out of the way. I'll leave that there just so we can cover stuff. Let's get rid of this stuff up here. Can't get rid of your stuff.
You can implement the zoom in a variety of ways. However, the method that will be beneficial for you for future tasks, and you won't have to modify it, is you specify a zoom level, which is an integer, so it can be 0, it comes here. Oh yes, it can. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, doesn't matter. And what happens to that zoom level is it's going to be put through an equation, which is 2 to the minus n, where n is the zoom level. And what that 2 to the minus n means is it represents the distance between each character or each pixel that you have. So the distance between each space in terms of mandelbrot coordinates. So say that my zoom level is 1, so 2 to the power of minus 1, that's a half. There's going to be half a coordinate, like half a mandelbrot coordinate distance in between each character. So,
as an example, we can actually have a look at what the implicit zoom level is for the program exercise that we've given you. Because we're fitting the range negative 1.5 to 1, because we're fitting that onto a canvas of size with x-axis of 72, then 72, is it 72 divided by 2.5?
Yeah,
is going to be...
It's 2.5 divided by 72.
2.5 divided by 72. Okay, cool.
And that'll give you the distance. I think this.
So we have 0.034. Because we have 2.5 units worth in the mandelbrot set, and we're displaying that over a discrete set of 72 points.
There's going to be
0.34 mandelbrot units
in between each
character here.
Yeah. And that's
pretty much zoom.
Now to the minus.
Yeah, what's that?
Yeah.
So if we were going to find that's 2 to the minus. Let's
just keep dividing by 2, or you could use logs. But
well, it's in between.
I think it comes.
So it's going to be like, yeah.
No, that's you're like
keep going.
A whole order of magnitude. I don't know how many zooms we've done. Oh no, I've reset. Either way, it's some zoom level. I think it's 7. 2 to the minus 7. Try that.
2 to the minus 7. Whoops.
Oh.
I'm terrible at using this calculator.
No,
this is not working out for me.
This isn't working.
Yeah, I can't really get that calculator to work. But I think I'm fairly sure that if you start with a zoom level of 7 or 8, that will give you the mandelbrot set fairly close to what we've done in this exercise. Now, you're probably wondering, okay, well, how do I implement that zoom level into the program? Well, that's the challenge exercise. So go away and think about looking at how we've done the scaling and how we've set the minimum and maximum x values in the task 1 and task 2, and then think about how the zoom level corresponds to that. So think you're mapping a certain amount of area onto a certain amount of area. A zoom level is you're simply increasing or decreasing the area that you're mapping onto a certain area.
Also, it's close to like zoom level 5, actually.
Zoom level 5. There you go. Karl with the answers. That's awesome.
I guess also something to keep in mind is the fact that whenever you're zooming in, you're going to be decreasing the distance in between each pixel. Characters both horizontally and vertically. So it's going to halve on the horizontal, on the x-axis, and halve on the y-axis. So what you're going to have is actually a quarter of the image you had initially.
Yeah, depending on the fact that you also have not a 1:1 on the width and...
Oh, what?
No, yeah, it depends. As long as the scale doesn't change, it should be alright.
Yeah.
So, yeah, what Karl is just saying is, if you have a 4x4, so say we have an asterisk, space, and space, and you're saying if you zoom, then suddenly this sector
could become
its own.
Yeah, and then you'd have 4 pixels for that 4 characters for what was initially just 1 character. Obviously, you have more than 4 characters, but yeah.
So this single asterisk here could represent a 4x4 area of asterisk, and a space. And the reason that is the case is because mandelbrot is a mathematical structure. It's infinite.
Yeah, every single point is infinitely small, so obviously we can't test every single point because there's an infinity of points. So you've got to take a sample of points, and for all intents and purposes, if we just made it just be 1 pixel wide, your eye wouldn't be able to tell the difference between whether or not we tested the points in there, because it's impossible. You can't display something smaller. So as we zoom in, we'll be getting more and more detail, because we're testing more and more points that are closer and closer, basically.
That's exciting, because theoretically, you could keep zooming forever.
Apart from the limitations.
The limitations of technology and software. Theoretically, if you could keep zooming, because between 2 discrete points, so there's an infinity of points in between those two, and that's a kind of cool idea. And that's one of the things that makes mandelbrot so freaking awesome, is that they're an infinite world where there's so much in there that people haven't discovered.
Yeah. And also the fact that in between those two, even if it's just a tiny distance, you're going to have something that's infinitely complex, and you can just keep zooming. Except obviously if you're like right in the middle and it's all just black.
Okay, so that's all the explanation we get from us today. We'll now move on to the cool stuff. If you've sat through the entire 45 minutes so far in the excruciating explanations that we provided, now hopefully some of you have got something out of it, and it has made some sense. If not, please feel free to tell us where we confused you, and we'll try and get on the forums and confuse you further.
Probably when we confused ourselves.
One of the difficult parts is once you've been through an exercise like this and you've done it, it's sometimes hard to remember
how hard it was for you. So.
How hard it is to understand the concepts.
We're just like, yeah, this is easy. We've already done this.
But I think scaling is one of the more difficult parts to understand with this. But once you understand the scaling and how you're mapping from one coordinate system to another, once you understand that concept, hopefully the rest falls into place. And the cool stuff that we're about to show you is related to the fact that right now, if everything we've said to you here makes sense, and you have, or if you, in the next couple of days, even, or no matter when you do it, once you've completed this task,
you can do it yourself right now. You have the knowledge needed.
Yeah, to do what we're about to show you.
Although we'll be also writing exercises so that you can do these cool things if you need help.
And in fact, some of these cool things we're about to show you are one of the things that you will be doing, as far as I'm aware in this course.
Yeah.
So it builds out of a few of the simpler exercises. So far you've done an exercise where you create a bitmap and you store some pixel data. You've got an exercise where you've served some HTML data or a poem via a web server, and now you've created an AsciiBrot in the terminal. If you combine all three of those things together,
you've got everything you need.
Yeah, I mean, what we're about to show you are some bitmaps of mandelbrots. And the pixel data, it's exactly the same. Whether you've decided to do an asterisk or a space, or like some of you have done and just gone above and beyond the task and created awesome animated mandelbrots in the terminal with coloring, that color value which you've calculated is based on, most of the time, the number of iterations or other mathematical features. So if you take that and convert that into pixel data, you can then create a bitmap and you can then serve that onto a web page with all the skills you have right now. And that's something that's pretty awesome.
And also, if you've seen the task from Module 8, where you had to explore the Mandelbrot set using the Almond-Bread web browser, you'll also be able to have something where you'll be able to go through the Mandelbrot set and just explore it like that. And also, you'll be able to fix the bug that was. We'll tell you the fix that will, that we think was the problem with Almond-Bread always crashing, and you'll be able to implement that so it doesn't.
Awesome. So here are some examples from our 1917 course, which is the UNSW
first semester course
for computing, which is pretty much what you're going through now.
First half of it throughout this course, and we'll also be hosting the second half of this course. As far as I know, Richard intends to have it online at some point in the future, but I can't.
Which will be very, very cool. So you have come a very long way. If you're still with the course, you're doing some really cool stuff now, and you have come a long way in your journey. We hope you've learned something along the way. And this is something to look forward to with the knowledge that you've gained so far. So these are some bitmaps of mandelbrots which were generated by students in our course. These ones were not generated by us. There is one which was generated with myself and my pair. We did this in pairs when we did it.
None of mine because they all suck.
So this one here is very interesting. I won't name the students who did it, but because I can't remember who they are. But this will show you that this is the exact same algorithm which you've used in AsciiBrot. This is the thing I want to hit home. The exact same calculation which you've done is what was used to generate this sort of a picture. The difference...
Yeah, the only difference is that they've implemented a sort of smooth coloring algorithm, which you won't be doing in the course, but you'll still be able to do something very similar to this one. If you want, you can even look it up on Wikipedia. The algorithms aren't that difficult. I think John implemented it in his, and as far as I know, it wasn't too hard, was it?
No, it's not too bad. You can... So this is the one that myself and my partner did. With a little bit of mathematics, you can generate something that looks like that fairly easily.
Yeah. And a bit of Google foo.
Yeah, so if you Google, there's lots of websites out there that go through how to do smooth coloring on mandelbrots. This one back here is a very original way of how to color a mandelbrot.
There was no use of smooth coloring or anything like that. It's just standard.
This was clever use of using modular arithmetic, more or less, to generate some really cool effects. Yeah, this is using mod. But yeah, it's something I've never seen. I've never seen anyone color it this way. And not just this image, but if you keep looking around the mandelbrot, one of the exciting parts is exploring it. This one has some really cool effects. So yeah, that's some of the cool stuff. I think we've covered all of the Maybe, maybe not.
Right, check.
It's broke.
Click it. Ah, this one's
So there you
really
go.
good.
This one's pretty cool. Yeah, it's very colourful.
Mm.
What you will find is if you implement smooth colouring algorithm, if you're at the top zoom level, it's pretty boring. And that is because most of the complexity in the mandelbrot is as you delve further and further. So if you implement some smooth colouring and it looks pretty boring from up the top, zoom in and you will be rewarded.
And if you still have no idea how to get started on this, don't worry, we'll have some activities up that will kind of guide you through the process of doing all this and generating these beautiful images.
So that's all from us. I hope you've got something out of the video. It is a long video. If you've been here the whole time and haven't just skipped through the whole thing, then that's awesome. If you have skipped through the whole thing, I hope you got the bits out of it that you needed. And as long as one person benefits from this, I think it was a success.
We'll have kind of some. If you upload it to YouTube, we'll have something where you can just click and skip to specific parts of the video.
That would be cool. That would be cool. And get George Clooney to do a voiceover, maybe, for some of the explanation.
Maybe. Probably Morgan Freeman. Actually.
Morgan Freeman would be good. Morgan Freeman and George Clooney. Okay, we're just rambling on now with stuff that you probably don't want to hear. But one thing we would like to catch up with you guys at the next Google Hangout. Those of you who aren't in the first cohort probably haven't, well, yeah, most definitely haven't seen the Google Hangout. We are going to be opening them up to all cohorts now.
Mm-hmm.
So information for when that's going to be happening will be on the Open Learning website.
Yeah.
We do apologise for the slow start to this year. There was a few things which are outside of our control, which has unfortunately delayed some of the modules.
Yeah, it's the start of the year, so it takes all the lecturers are trying to organise the course and every courses that they're going to be teaching and everything, so it's hard work.
And everyone working on this course, you may not be aware, but everyone working on the course, this is not their main job, or this is not their main thing. So myself and Karl are students. Most of the other tutors are students who are just about to go back to uni. A lot of the other staff are full-time lecturers or in other full-time positions which require their work. But that doesn't mean we're not dedicated to doing this course. We are, and we are keen to get back on the forums and chat to you guys and see what you guys are able to do with the next task 2 coming up. So with that,
have a good one.
Bid you adieu. Catch you guys later.
See ya.
Bye.
I reckon that was good.